Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. What's new in the world of science for you?
Well, it's nothing particularly groundbreaking, but a nice little story. Over in Alberta in Canada, a few days ago, a small asteroid, about 10 tonnes of rock, basically hit the atmosphere, came down like huge shooting star, some lovely videos of it on YouTube, came down, huge glowing ball of fire and light, then exploded.
Right.
Then all these 10 tonnes of rock have kind of got scattered all the way over Alberta, farmland in Alberta.
Yeah.
And so various scientists have been wandering around Alberta trying to pick up these bits of rock. They've basically, and it's a lovely time to do it because it's very cold in Alberta this time of year. So all of the kind of water and all of the parts of the asteroid which would boil off very quickly if it landed in this sort of atmosphere, because it's sort of minus 20 in Alberta, they're staying frozen in there, so it preserves the asteroid much better.
Yep. And
so they've been wandering around. Apparently they reckon there's about 10,000 bits lying around Alberta. The scientists have found at least 60 or 70 of them without trying very hard. They think it could be quite important because from the way it came down and with some tracking data before it actually hit the Earth's atmosphere, they can work out what its orbit was, and then they can sort of play its route backwards in time for a few thousand years and work out where it came from. And this means, and it's very rare that you actually get a meteorite which you can tell where it came from in the solar system. Mm-hmm. I think there's only about 7 meteorites in the past they've been able to do this from this, and lots of other ones in the future. They'll be able to start building up a much better picture of how the solar system started. But mostly I just like the image of lots of Canadians running around the farmland looking for bits of rock falling out of the sky.
Absolutely. There was no damage done to anybody, was there?
Nothing serious, no. The biggest lump they've found is 13 kilograms, but I guess it landed in the middle of a field.
Yeah, let's hope so. Anyway, it didn't do any damage. Our first question then for Naked Scientists. Dr. Dave, you asked the question. This one is from Andrew Dave. Andrew in Cambridge says, how does a spy satellite work?
Well, a spy satellite is basically a satellite, so it's orbiting the Earth. A lot of them tend to be orbiting quite low down, so they're as close as possible. So they tend to be on very elliptical orbits, the ones which get really detailed pictures, so that they'll sort of fly down very close. They'll sort of be grazing the top of the atmosphere, maybe only 200 kilometres up at the closest point of their orbit. And then you have various different sensors on them, mostly just very, very big telescopes. They put sort of telescopes with a 2 or 3 metre aperture on the front of them. And then they're basically just looking down at the Earth and then beaming the pictures they take back to their base. A lot of what you see on films, I think, is a bit of an exaggeration because they tend to be able to take a satellite and then say, right, we want to be able to see this now, and then you get constant satellite coverage. But actually, these satellites are whizzing around the Earth all the time, so every 90 minutes. And so for a start, they've got to be on an orbit which passes over the place you want to look at. And secondly, they're not always over that at any one time. So although you can get very, very good pictures, you don't get them all the time. You don't get a constant video information. So you basically occasionally get some very detailed pictures. I think they can use colours of light to look at things which our eyes can't see, things like infrared light and ultraviolet light, some of which will go through cloud better than visible light. So they have some advantages in looking through clouds. Other ones, I think they've probably got some radar-based ones, which will go straight through clouds, so you can build up a kind of 3-dimensional picture of the ground, even if there's cloud over the top. And probably you could then see if something was moving, but again, it's not going to be nearly as detailed as the visible light ones. So basically just big telescopes orbiting around the Earth, but they do have more sophisticated things. I'm sure the Americans have been spending their billions of dollars and got something for it.
All right, Andrew, I hope that's answered your question. Let's stay with all that satellite stuff. Mike in Colchester says, as we know, sat-nav is becoming more and more popular. Yes, the prices are going down, aren't they? Is it true that America have control of the majority of the satellites that provide for these sat-nav systems? Also, in theory, could they turn it all off?
It is rather, isn't it? The simple answer is yes. At the moment, and all of the sat-nav systems you bought now are running off an American military system called GPS, the Global Positioning System. It works by having lots of different satellites orbiting, I think at least 18, if not more, orbiting around the Earth, quite low down, and they've all got very, very accurate clocks on them, and they're sending out little radio pulses, and then your little sat-nav, you longer for the pulse to get to you. And from these minute changes in time, your nav systems are incredible. They can be so accurate. It's working out from these differences in time it takes for the pulses to get to you, it's working out where you are. And yes, it is a military system, and the Americans do have the power to turn it off. Until quite recently, they scrambled the most accurate, basically that they give you a position to within 100 metres, but they would scramble the last sort of couple of digits of the data. They stopped doing that recently, and I think they've said they probably won't turn it off, but there is nothing to stop them switching the switch. I think occasionally they do switch the switch in an area, so all of a sudden Afghanistan suddenly becomes a lot less accurate. So you might be able to tell your position to only within a kilometre in Afghanistan because the Americans have put it sort of encrypting, the sort of coding the last few digits of your position.
So an atlas or a good road map then is always a good present.
Good backup, yeah.
A bit cheaper as well.
Harder work, but definitely worth having.
We have one here from Tony in Chelmsford who says, Dr. Dave, if you put a cane through a football and spun it, anything that was on it would fly off. Why is this not the case with the Earth spinning?
So what I think Tony's talking about is centrifugal force. Now, it's not really a real force. It's what physics teachers call a pseudo-force. Basically, if you're sitting on a roundabout, you maybe did this when you were a kid, if the roundabout's going round and round and round really fast, you feel like you're being thrown off all the time. Actually, you're not really being thrown off. What it is when, if anything with mass, so you've got mass, what it wants to do is carry on going in a straight line at a constant speed. And if the roundabout's making you go around in a circle, you need a force to make you go around in that circle. And so the roundabout's pulling on you in order to make you go in the circle, and so you feel like you're being thrown out compared to the roundabout because you keep trying to go in a straight line. And now if something's sitting on a ball that's spinning, all the objects on the ball are going to want to carry on going in a straight line, and so they'll sort of fly off. So if you spin a plate really fast, all the things on it will fly off because they'll get sped up by the plate spinning. They'll try and going in a straight line and fly off the plate. Now, on the Earth, that is an effect. The Earth is spinning and everything is trying to carry on in a straight line, so essentially it feels this pseudo-force, centrifugal force, so it does feel like it's being thrown outwards. In fact, that's why the Earth is bigger around the middle than the radius of the Earth is bigger to the equator than it is to the North Pole, because the centre is being thrown out. But because the Earth is actually spinning not very fast compared to the amount of gravity it's got. Gravity is much larger than this effect. It's less, it's the most a percent or two. I'd have to do the calculation, which I can't do in my head while talking. And so it does affect your weight. You are lighter when you stand on the equator than on the North Pole, because you're getting thrown out, and also because you're further away from the centre of the Earth.
Wow.
But it's not nearly as much as the gravity pulling you in, so you're just pulled in slightly less strongly than you would be otherwise.
All right, that answers that one. Now then, we have Mike, who says that he recently read that there are around about 30 million counterfeit £1 coins in circulation. How can we tell which are the counterfeit and which are the real ones? Do you know about coins?
I don't know about coins. I know various security features in notes. There's all sorts of lovely ones which I know about. For a start, they're very, very intricate. And there's some things, you've seen the things in pubs and clubs and things, whereby if you put a £5 note under an ultraviolet light, it will there's two things. One, if you put normal paper under ultraviolet light, it's got this sort of optical brighteners in it, which are the same things which they put in washing powder, which makes people's bras glow under their tops, which you may have noticed in the past.
Dave, no, I don't go around looking at other people's underwear, but thank you.
Okay, fair enough.
Yeah.
Basically, they put stuff in washing powder to make it look whiter than white.
Yes.
And they put the same thing in, which takes ultraviolet light and converts into a blue glow. So ultraviolet light which is invisible, gets converted into normal light, which you can see. So it looks like your clothes are glowing. They did put the same thing in paper. So if you photocopy a £5 note onto a piece of paper and you put it under ultraviolet light, it will be glowing really brightly, but real £5 notes don't glow. And they also write things in inks, which you can only see in ultraviolet light start glowing. There's also some really neat things whereby if you look at it in infrared light, near infrared light, half of the Queen's head disappears.
All right.
Which is really wacky. But I don't know about coins. I guess it could be on the if the masses are slightly off, or if they just don't look right. I don't know if there are any other subtle ways of telling. It could also be that if you look at the metal very carefully, if you analyse the metal inside the coins, that counterfeits are normally a different kind of metal structure than normal coins. I don't know how to tell other than that, I'm afraid.
Right, Petra asks, all planets in the solar system rotate anti-clockwise except for Venus. Why is this, Dr. Dave?
This is an interesting question, and I think lots of scientists think it's a very interesting question as well. Yes, pretty much, if you're looking from the Earth's North Pole, then pretty much all the planets rotate anti-clockwise, apart from Uranus, which is sort of 90 degrees for everything else, so it's virtually, it says orbiting on its side, this is spinning on its side, so it's not really orbiting clockwise or anti-clockwise, it's so far off, knocked over to one side. Venus does seem to be rotating the other direction. It's spinning about once every time it orbits around the Sun. There have been various theories about this. One of the older ones is that actually the time it takes for Venus to spin round is pretty much exactly 2/3 of the time it takes the Earth to orbit the Sun. And you can get some strange effects whereby the time it takes for something to spin it will become sort of locked with something else moving around. So if you've got something orbiting a planet, a moon orbiting a planet, sometimes you do get them spinning about once and a half times every time it rotates. So people did think it was something to do with a locking effect between the Earth and Venus. Every time it came near the Earth, Venus is probably flattened a bit into a little bit of an egg shape, and it's energetically favourable for the egg to be pointing towards the Earth every time it meets. And so if it spins one and a half times every time the Earth goes around, then it would be. So that might be one thing, although I think apparently more recently people think it's likely to do with large impacts, that if Venus wasn't spinning very fast to start with, then if it got hit by something large and heavy near the beginning of its career, as it were, it could just sort of on the side, then it could just hit it on one side and it'll just start it spinning the other direction. But like if you've got a roundabout and you run into it from one direction, then you're going to start it spinning in the direction. Even if it's spinning slowly in one direction, if you bash into it the other way, it's going to spin the other. It's going to reverse its direction. To be honest, I don't think scientists really know.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. OK, here's another one here from Ian this time. He asks, how do we know that the centre of the Earth is red hot when we know some volcanoes spew out nowhere near from the centre? Can you clear this up, please, Dr. Dave? And if it is a ball of fire, why is it still hot?
OK, yes, we do think that the centre of the Earth is very, very hot. Pretty much all volcanoes, the rock they're coming from is coming from quite shallow, especially kind of volcanoes which the traditional ones you think of as a volcano, the nice cinder cones, nice cone-shaped volcanoes which go bang every so often, things like Mount Etna in Sicily. All of the kind of stereotypical ones, those are actually made, the rock which is coming up out of those is actually from the continents. So it can only come from maybe 10, 20, 30 kilometres down. It sort of gets sucked down in a subduction zone, and then because it's less dense than the mantle below, the Earth is sort of split up into a crust and then a mantle below it. It's less dense than the mantle below it, then it sort of floats up, it melts, then it sort of floats up again through the crust and forms volcanoes. So those come from very shallow. Probably the deepest volcanoes are from things like Iceland, where you've got a mantle plume coming up. This is a sort of hot bits of the mantle sort of float upwards, and so some parts of the mantle are floating upwards and other bits of the mantle are floating downwards. This process takes millions and millions of years, but you do get very, very hot regions. And then the least dense and the easiest melting bits of the rock from the mantle then kind of get squidged out. It's only sort of about 5% of the mantle rock gets squidged out and comes out in places like Iceland. There's another one, I think, under the Rift Valley in Africa, which is actually what's sort of melting Africa, and then it's sort of splitting it, sort of melting it, and then it's splitting apart, creating this valley. Eventually Africa's going to split into 2 continents. But yeah, that rock's coming from deeper. In theory, some of that could come up from several thousand kilometres down, but not from the actual core itself. The reason why we think that the core must be very hot is because everything around it is very hot, and it's been sitting there for 5 billion years. And if everything around it is hot and it's been sitting there for 5 billion years, it's got to be hot, because there's no way it can lose heat. It must be it must be hot. It probably ought to be hotter than the stuff around it. Why is it still hot after 4.5 billion years, or the age of the Earth? Well, there's 2 effects. One is that the Earth is very, very, very big, and so the rate at which it's losing heat is very slow, and it would still be quite warm after this amount of time. Even if you just heated it up 4 billion years ago, it wouldn't be cold by now, because there's 5,000 kilometres of rock, 6,000 kilometres of rock to the centre of the Earth. It's going to take a long time for the heat to diffuse out from the centre of the Earth. It's basically very well insulated. But the other effect is radiation. The Earth has got a load of uranium in it, thorium, other radioactive elements, and they're sitting there and slowly decaying away. It's not like a nuclear reactor whereby one nuclear reaction triggers another one, which triggers another one. They're just radioactive elements will just sit there and eventually, after a few billion years, just decay. And that releases quite a lot of energy. And in a lump of granite or something, the rate at which it's losing it, because the granite isn't very well insulated, it doesn't heat it up very much. It will heat it up a bit. If you drill down into a lump of granite, it'll be a few degrees centigrade, even 10 degrees centigrade hotter than the surrounding rock, but not very much. But if you've got something the size of the Earth, it doesn't lose heat very well. So it basically stays very hot. This basic nuclear reactor is keeping it warm. So I think the exact how much is nuclear reaction, how much is what's left over, I think the numbers I've heard is about 50-50. It could be a bit off that. It's a very rough estimate. But yeah, basically it's still hot because it takes a long time to cool down, and this nuclear reactor effect.
Good stuff. Thank you very much. Thank you to Ian. Our next question. I did ask people earlier on if technology had failed them at all today, and there are some strange things. Fergie says, technology failed me today when I could not turn on the CD player because it works from a remote control, and I could not find it. It seems that if you turn off with the remote, you can only switch it on with the remote control. But also, why is it that? Because if you lose your remote control, you are, everything renders useless, doesn't it? Why do they do that?
I think a lot of it is, it may sound stupid, but because switches are expensive.
Right.
When you compare with especially if you've got individual switches, they're compared to the price of electronics, which can all be done maybe with robots and set up very quickly, and you just sort of pile a load of bits in at one end, and CD players come out the other end. Actually, switches, especially if you have to hand wire them, or even if you don't, you've got to put them into a case. Everything's awkward, strange angles. You probably do have to do it by hand. They're actually very expensive. So companies tend to try and minimise the number of switches, the number of separate parts in the thing they make. Whereas a remote control, because it's not individual switches, it's all sort of made up of a big. In fact, they tend to have a sort of rubber sheet with little conducting bits at the top of it. A sort of bumpy rubber sheet, and with conducting bits in the tops of the bumps. And then when you push that down, it goes across 2 bits of copper on a board. So you can put lots and lots of switches on a remote control without making it much more any more expensive at all. But if you want separate switches on a box at the front of your room, It does cost more money, and so they don't, although it would make our lives a lot easier if they did.
Wouldn't it so? And also we'd be able to turn it off and save some energy.
Or for the 10 pence or whatever.
Yeah, exactly. Well, every little helps, you see, doesn't it? Another Mike has said, is it true that water will drain in opposite directions dependent on the hemisphere where it's in? Dr. Dave.
The simple answer to that is practically no, but in theory, yes. The reason why everyone says it does is that the Earth is spinning, and if you imagine the Earth spinning away in your head, and if you look at it from the North Pole, if you look at it, it's going to be spinning anti-clockwise, but if you look from the South Pole, because you're looking at it from the other side, it will look like it's spinning clockwise. And now if you imagine having a really big bathtub at the North Pole, and then all the water's starting off out thousands of kilometres out, and it's all running in towards the centre, and then falling down a hole in the centre, down a drain in the centre. It's going to start off spinning. It's going to be moving slowly because the Earth is spinning, but it's actually going to be moving quite fast. It's actually, if it was down at where we are here, we're moving at 600 miles an hour around the Earth all the time. So if it's moved in from 600 miles an hour, moving in towards the centre, it's going to be spinning really, really fast once it actually meets that plug hole. And so it's going to spin faster and faster as it comes in. And if you had something that big, it would always spin anti-clockwise in the northern hemisphere and clockwise on the southern hemisphere. The problem is that the smaller you get, the smaller bathtub you have to start with, the less this effect is. It's called the Coriolis force, which makes things spin as they move in towards the centre. And the smaller you get, the less effect there is. And also the further away from the poles you are, the less effect there is. So if you're near the equator, there's almost no Coriolis force. Things aren't going to spin. In fact, hurricanes can't form right on the equator because there's not enough. So when air moves in towards the centre, it doesn't spin, so you don't get these big winds. So you don't get hurricanes forming near the equator. They can only form sort of 10 or 15 degrees north or south of the equator, because then air is sucked in from thousands of kilometres away. It slowly spins faster and faster and faster, and you get a hurricane. But on a bathtub scale, someone has done it by getting a bathtub about 20 feet across, filling it with water, left it to stand for 2 weeks, and then taken the plug out very carefully, and then it does always spin in the same direction. But with your actual bathtub, it's going to be affected far more by which tap you turned off last, how you got out of the bath, whether you could have swirled it one way when you got out of the bath and swirled it the other way. And all these effects are far, far bigger than this Coriolis force. So in theory, yes, it does, but in practice, it's all to do with which way around it's probably more to do with which way around the taps are and which tap you turned off last when you take out the plug.
Now then, what else have we got here? Oh, Mr. Ed said, yeah, it's one of those things, isn't it, with computers and things. He said, I've only just been able to open my mail, my Yahoo Mail today. It wouldn't open at all this morning. Finally deleted it and reloaded it. It's working fine now. Why do computers do stuff like that sometimes?
Mostly because they're hideously, hideously complicated. Speaking as someone who spends most of his life programming computers, they are far more complicated than virtually anything else that which you come into contact with on an everyday life. A normal computer, just on the little tiny processing central CPU, the processor in the middle of it, it's got billions of switches in it, billions of transistors. And the software which they're written with, basically, it's very, very difficult. People try very hard to get it right, but they don't always get it right. So you get bugs in there. So I mean, and you could probably, in theory, get a piece of software which would work all the time if it was just that piece of software. The problem is you have a computer and it's got other programs running somewhere else which somebody else wrote. And even if the two pieces of software are perfectly fine on their own, you might find that they interact in strange ways you didn't expect. So one of them might be trying to do something when the other one assumed that it could. So program A might be trying to access a disk, and program B assumed that it would be able to get at the disk, but program A is doing it, and it can't. And so all of a sudden program B falls over because it's trying to do something which program A is already doing. And then, so even on a single computer, it's very hard to, because it's so complicated, it's very hard to make it predictable and reliable. And then you take something like the internet, which has got thousands and millions, if not billions of computers on it now, all at least as complicated as the one in your room, all interacting. And they're not just interacting in nice ways and accidentally going wrong. There are people deliberately out there trying to hijack computers,
mess you up,
trying to mess things up, deliberately trying to knock down websites so as they can extort money out of the website owner to stop doing it, and things like this. So basically, it's just a huge, scary, complicated system, and they don't always work. People try very hard, and it's amazing how much of the time they do work.
This is it, you see. Technology does cost us a lot of time. Right, OK, let's have some more questions now. One here, if I stand in my hall with my digital TV and analogue TV on, there is a time delay on the pips, etc. Which is the accurate time? Good one.
I think at the moment the analogue TV is a lot better. Is a lot more accurate. The digital TV, basically, what they're trying to do is squeeze more information into less space. You've got a certain amount of what's called bandwidth. Sort of imagine TV channels. You get a certain amount of TV channels in the amount of radio space there is. And digital TV squeezes more into the same space. And the way they're doing this is by, instead of transmitting a whole of a picture every frame, so 50 times a second, 60 times a second, 50 times a second in the UK, they only transmit the changes. So occasionally they'll send a whole frame of a picture, and then they'll just send the bits which are changing. And seeing as most of TV, mostly the screen is staying still, and you only get the odd changes, that saves a lot of space. And they do all sorts of clever things like spot whole objects which are moving and try and save space by saying this object is moving and things like that. And the problem is this takes time. It takes a lot of processing to do. So both to encode and decode. So it takes a couple of seconds, so it slows things down. And the other problem is I don't think it's necessarily entirely predictable how long the slowdown is. So they can't just offset the pips to be a bit earlier. Send them a bit earlier at the beginning, and then they come out at the right time. So the analogue one is more accurate.
The analogue one is more accurate. Hurrah! Thank you very much indeed. Phil has called in. He says, has Dr. Dave seen the advert with the phones as dominoes? He wants to know if it was kept going, would it ever lose momentum?
I haven't seen the advert itself, but I'm guessing he's basically saying if you've got dominoes, would they ever lose momentum? The answer is if you set them up right and you've got enough dominoes, not really, no, because every time a domino's got more energy when it's standing up than when it's lying down, and so every time one falls over, it releases a bit of energy, and some of that energy gets transferred to the next one, which then releases a bit more energy as it falls over the next one, and the next one, and the next one, and the next one, and the next one. As long as you don't have a thing whereby it doesn't have enough energy to knock over the next domino, it should keep on going as long as there's energy to release there, as long as there's another domino in front. So I don't know if you've seen the advert itself. There's no reason why it shouldn't keep on going until you run out of phones, I guess.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.